Welcome to another episode of The New Quantum Era. I'm your host, Sebastian Hassinger. This is episode 50 of the podcast, For Real. Repeat listeners may recall I inadvertently called episode 48 episode 49 and then corrected myself in episode 49. I assure you that this is definitely episode 50. It feels like a milestone of sorts, despite just being an arbitrary number that feels important because it's evenly divisible by 10, which is the number of fingers we have. But nonetheless, I really appreciate all the collaborative effort that Kevin put into the first 35 or so episodes, and he continues to be a collaborator and a supporter, and the work that Omar put into the awesome theme music, which, by the way, includes the sound of dilution refrigerators in the background, and the ongoing help from Ian on the production end of things. I'm very grateful to all our guests taking the time to talk with us and to help explain this often mind-bending subject, and of course, all our listeners. I love seeing the downloads line going up and to the right as time goes on, and I'm excited about what the future holds for this project. So today's episode was again recorded at the American Physical Society's Global Summit with their kind support and with support from Quantum Machines. I'm joined today by Dr. Anna Grassellino, director of the Superconducting Quantum Materials and Systems Center at Fermilab, known as SQMS. Fermilab is formerly known as the Fermi National Accelerator Laboratory and is, of course, one of the treasures of the American scientific community. Established in 1967 in Batavia, Illinois, and renamed in honor of Enrico Fermi in 1974, Fermilab is one of the U.S. Department of Energy's national labs focusing on high energy and particle physics, among many other scientific topics. The SQMS Center was founded as a part of the U.S. National Quantum Initiative and brings together over 500 researchers from 36 participating institutions across public and private sectors. The focus of the center is on multidisciplinary collaborations in quantum information science, material science, applied and theoretical superconductivity, computational science, particle and condensed matter physics, cryogenics, microwave devices, and controls engineering. And we're very pleased to be joined by our guest, Dr. Anna Grassellino. Anna, thank you very much for joining me.
Thank you for having me.
That's great. So we're here at APS. I saw your session yesterday that was part of the NQI Center's sort of retrospective, and I thought it was really interesting. I thought really what distinguished your presentation was a very intense focus on increasing coherence times. And that's clear from the results you've gotten at SQMS. But tell me a little bit about, it's sort of a multi-pronged strategy to examine a number of different ways to attack that challenge, right?
Yes. It's been a really exciting journey. We really put together a coalition of experts at 360 degrees to attack decoherence in superconducting devices, in superconducting qubits. Like you say, it's a multi-pronged strategy. We built the center around the fact that actually my background, and I think that's really what's important. To be an effective director, I think you have to be excited about the mission of your center. I spent half of my career actually doing that, pushing coherence, the quality factor of cavities, making them, how do we make superconducting cavities as efficient as possible, right. Less lossy. Where are these losses coming from?
And that was in the context of particle acceleration, right? I mean,
correct.
That was okay, great.
Exactly, for particle acceleration, and actually we built an entire light source at SLAC at Stanford with our technology, where we pushed the coherence, the quality factor, a factor of 3, with in fact some very small, subtle tweaks in the impurity concentration in the first, let's say, 100 nanometers of the surface of these devices. And so in a similar way here, we have adopted this approach of hand-in-hand the material science, the nanostructure, the superconducting properties, how do they tie? Can we push for a really fundamental understanding of how they tie to the device performance? The multi-pronged approach you were mentioning, to me, what works always best is you must push to do novel processes, novel things. Sometimes you are right about what you're trying to get, and sometimes you get something completely different, but that's how science works.
Yes.
When you study it in detail and you develop a novel understanding that then guides really the performance in a systematic way. And so our approach at SQMS has been, as I explained in my presentation on Monday, we have created several task forces and cross-cutting groups across the center. One that I'm particularly proud of, for example, this National Nanofabrication Task Force, where we've got experts from industry, from research foundries, and they work really hand in hand, and they look at changing processes when we fabricate these devices by changing one variable at a time, if possible, for example. And then hand in hand with the materials task force, where once we make a new device, then it goes and it gets reviewed by experts in a variety of techniques, surface analysis techniques, from the most conventional SEM and TM, then taking these techniques down to cryogenic temperatures. I think this has been a very important point, not studying just with microscope, but at the temperature, at the
operating temperature.
The operating temperatures. And then really also looking with things that are a little more exotic techniques, including muon spin rotation, telluride spectroscopy. And we have gained a lot of novel insights, and then feeding all this knowledge back into how we fabricate, how we move forward with the next steps.
You mentioned sort of the degree of collaboration across industry as well. I know Rigetti in particular. I mean, a number of industry partners are active at SQMS, but Rigetti has really been integrating a lot of your findings in their own design and fabrication, right? It's almost a partnership more than a collaboration. Like they've been getting direct sort of value out of that relationship, it seems.
Yes, I think for me, this has been maybe one of the most successful things. So when we went into this initiative, I guess one question, and the initiative of this center is really bring together national labs, academia, and industry to move forward together. But has always been a question mark. How much will industry be open, right? With all the questions around IP, right? But I think with Rigetti has been a super successful collaboration model where we have been really open with each other. They've been really open with us, with our SQMS partners, and that's key. That's essential to really then being able to make progress together. But yes, so. Some examples include, for example, the studies on encapsulation, where we understood that the surface oxides were very lossy, and we wanted to replace niobium oxides with less lossy oxides, such, for example, as tantalum or gold or other type of encapsulation strategies. So we did it first at Fermilab at the University of Chicago Pritzker nanofabrication facilities, and then when we saw the success, we repeated in the commercial foundries at Rigetti. They saw actually the same successful doubling of coherence times on their silicon-based qubits, which for us was really fantastic success to see indeed that it reproduces in the commercial settings. Other things included, for example, some different chemical processing of the silicon surface. This was in collaboration between Rigetti and our Northwestern partners, where Professor Marcus has been leading how we passivate silicon to create a less lossy silicon oxide. And these findings have been implemented actually in Rigetti processes. The ABA, the annealing of the junctions that Dave Pappas has been leading at Rigetti, for example, which gave more systematic, really much more systematic performance of these junctions. This was also a very strong collaboration with Ames Lab, where Ames was leading the characterization and really the understanding of what this novel treatment is actually doing on a nanostructural level. So there are numerous examples of where really we have been successfully working together and integrating things directly into their processors.
And a lot of that has to do with Transmon, designed superconducting qubits, but you've also done a lot of work at SQMS on ultra high Q superconducting radio frequency cavities, right? Which are more, I guess, derived from those super colliders, like the equipment that you would need for that type of use case. What's the applicability of those cavities, those devices to either quantum computing or quantum networking, quantum memories, that type of application?
Thank you for asking. Yeah, so this was actually, in fact, the central theme. And then I think everybody got very excited about the materials and the transmon qubit. So a lot of effort actually went into that. But really, the thing that we said, again, going back to these initiatives are only successful, I think, if you build it on who you really are and what your strengths are. So we viewed ourselves at Fermilab as the place where we make the best cavities in the world. I mean, without exaggeration, we have been able, before the center started, we demonstrated niobium three-dimensional resonators with coherence times of 2 seconds in the quantum regime. So this was very exciting.
That's 2 seconds, not milliseconds, not microseconds.
Exactly. So this is
whole seconds.
So then the idea is to pursue this cavity. So this is for empty cavities, right? Now you want to turn it into an actual quantum device, so you have to non-linearize it. So you have to couple it with some element that adds the non-linearity. So the idea here is to really couple cavities and transmon qubits. It doesn't have to be a transmon qubit; it could be something else. But currently, that's what we are doing. And then you turn this structure into an actual qubit. So the idea is to actually build D levels. And that is only possible because of the very high coherence of the system. So 5 years down and that ties it together with the theme, though, of improving the transmon, because ultimately, if the transmon can become the bottleneck dragging down the overall coherence of the combined system. So really, that's how the center come together cohesively. We improve the transmon for helping the community, for helping industry, for chip-based architectures, but at the same time is the ancilla for the architecture that we want to drive for quantum computers. And so 4.5 years down the road, I think we're very excited of the recent results that we showed. We have demonstrated a double cell. So this is Alice and Bob talking to each other with a first gate fidelity that we quote at 99.8%. And we are able to build very large Fock states above 30 Fock states with coherence of milliseconds. So that's a really exciting thing. So we think that there is a lot more research to do where we could, for example, could expand and package more modes into these structures. So we think, when people think about these cavities, they see them as large, bulky, do they really scale? But actually the scalability is in the coherence. Is in the
and the multiple states within the one cavity.
Within the one structure, exactly.
And does that make it more conducive to say, memory or networking applications?
So that could also be, we have not explored the angle of using cavities as in the repeaters, but that can also absolutely be a very important application. So we're very focused on building an actual quantum computing prototype that is based on these cavities. But yes, the memory part is also an important application that we will perhaps explore in the future.
That's cool. And I mean, everything that you're describing, of course, there's experiments, there's efforts, there's innovation that you're describing that's directly carried out by people at SQMS, partners with SQMS. But in addition, the national labs are an incredible sort of investment in infrastructure for the scientific community, and that the NQI centers feel like they're extending that to infrastructure for the quantum computing or the emerging technology around quantum science and technology community. The example I'm thinking of is the quantum garage. I mean, you're building, sort of resources and infrastructure that are helping anybody working in the quantum community, really. I mean, can you tell me more about that garage?
Yes. Thank you for actually looking into all the details of the things we do. But absolutely.
I didn't do it just over the last couple of days. I've been watching what you've been doing at SQMS for years now. So.
Thank you. Absolutely. We view these, of course, we are excited. So that's the number one. We want to push the technology, but it is a service to the field. It's a service to the community. And of course, it is also a little bit selfish because we do want to use these tools to discover new physics, right?
Yeah.
I mean, that's an important motor
Right.
that I do want to mention. We do have a lot of part of when we built the center was the excitement across Fermilab, from the theory division, from the particle physics division. These are going to be novel tools that will help us advance our mission of, understanding the universe at a
Right.
smaller scale. But yes, back to the service to the community. The idea of the garage was, first of all, to advance all the goals. We simply needed to be able to have more throughput,
Right.
and so we did. We added a fleet of 6 dilution fridges, which though we do make, and now we make available to the community. Again, not open in a very open way to the community in SQMS, but we of course also say that if people see value in the special tools that we have, that can be cavities to measure. Let me just give an example. Part of the things that we deployed at the garage is using SRF cavities also as novel tools to characterize dielectrics, like the substrates, for
Right.
example, with parts per billion precision. Because these cavities have very, very high quality factors, you can actually use them as sample hosts. And so places like Kyocera that makes substrates like sapphire and other type of substrates for quantum computing chips, they've come to us for helping them characterize
Right.
their substrates. That's an example where they weren't part of SQMS, but they saw a unique tool in
Right.
what we offered at the garage, and there was definitely bidirectional value there because together we can push,
Right.
And substrates, low loss dielectrics continues to be a really, really important topic for pushing further coherence of superconducting qubits. So that's just an example. We have had startups that wanted to test their control hardware, and we have a little QPU that we co-developed with Rigetti, a 9-chip one.
Right.
And they can come and hook up their hardware. There are some areas where we see value in helping beyond our partners. One area where I really see that the national labs like Fermilab shine in terms of service to the community and helping advance critical technologies for quantum is the cryogenics. So that's actually even beyond the garage, but as you may know, Fermilab has really huge facilities in terms of low temperature cryogenics. We have cryo plants that are just sitting around that
Right.
were used for some experiments, but the experiments now are finished, and so they're available.
Right.
So there is a huge amount of expertise in cryogenics and ultra low temperature cryogenics. So part of what we are doing, for example, is taking this expertise, taking these facilities, and putting it to the advancement of ultra-low temperature technologies for future large-scale data centers. So one of the things that really excites us, for example, is our recent partnership with Maybell.
Right.
They are a wonderful company that is growing in the U.S. in this space, and
It's good to see more fridge manufacturers coming out.
exactly. And so,
As you said, eventually we're going to be filling data centers with these things. We need a lot of people building them.
and so there, a critical technological obstacle is when you need to move to a farm of, let's say, 50 to 100 fridges. It becomes, from the point of view of power consumption, it
Right.
becomes economically really disadvantageous.
Right.
Unless you actually directly connect to a liquid helium cryo plant. And so this work of liquid helium cryo plant to millikelvin has been something that we have done research on at Fermilab. And so with Maybell, we plan to actually now work together to bring this technology that we have advanced to become a commercial reality here in the US.
I guess I hadn't thought of that. The dilution refrigerator is really designed from the ground up to be almost a standalone experiment, not a deployed technology. So once you deploy it in mass in a data center, you're going to have to think about your cooling infrastructure as a whole facility, not as a standalone.
Correct.
That makes total sense.
When you want it, it's great that they're standalone. It makes it,
Sure.
it brings the ability to do this type of experiments in a basement or a university. So
Right.
that's great. But like you say, the data centers are going to be something completely different. So that's something, again, where now we are discussing to bring, for example, a farm of fridges to do a validation of these technologies, for example, at Fermilab. So Maybell could bring a fleet, for example. So just in answer to your question, where national labs can shine, I mean, this is kind of who we are.
Right.
Large-scale facilities, system integration at very large scale. It's our bread and butter, going back to who we are.
Right.
We build accelerators on kilometer scale with this cryo distribution system that span kilometers. So.
Well, and it's so interesting. I mean, I think one of the unique sort of characteristics of this point in time is that you have all that sort of big science experience and infrastructure as the national labs, and those types of that scale of investment in basic science is really the public domain, right? It's for the public good. It's driven by the public sector. But in this instance, we've got also the private industry, private sector, looking at seeing this as being a technology with incredible applications in the future. So you're really, leveraging science infrastructure to bootstrap early stages of a new technology. And I think that's really, we haven't seen that in many decades, I think, in this way. So that I find super, super interesting, and why I find the DOE and QI Center is so fascinating. You're sort of at this point where you're, the Monday session was almost a retrospective of what you've accomplished over the last 5 years, because there is this NQI reauthorization upcoming, and the centers are sort of having a chance to go back to their proposals and think about the next 5 years. So what do you see as being in 5 years' time, what do you want to look back on and see that you've accomplished at that point?
Yeah, thank you for the question. No, first of all, yes, I think the Monday session really offered us an opportunity at taking a breath and looking back, and we definitely accomplished a lot. I think there was a question at the end of the session, which was, are we doing everything? Is there something we are missing? And I think it goes a little bit along what you are saying now. So 5 years down the road, looking back, what is really important? So, and I answered on Monday saying, and I will say again today, there is definitely strong push and appetite to move to systems. We spent a lot of time in the first 5 years really attacking, at least at SQMS, attacking decoherence. And I think this is really, it continues to be really important. Yeah. I mean, and I actually think it will be dangerous if we say, oh, that's all taken care of, it's solved, it's not a problem. I think sweeping things under the carpet will always come back and bite us. Yeah. So that needs to continue. Attacking decoherence will simplify our life in terms of how large these systems are going to have to be. Right. But it's true that we must build systems. We cannot continue to, focus only on the fundamental science aspect. I think the NQI reauthorization has explicit language now pushed towards engineering systems and applications. Right. So again, the real challenge now is going to be balancing those things, in my opinion. We do want to build a system. So if we take the cavity results, I think we feel now that we have some solid sort of building blocks that we can start to scale up. Of course, everybody wants to make it even better. So, but is this the perfect building block before we build a prototype that is, let's say, 100 qubits? And so that's where I'm pushing our group to say, everybody starts from somewhere. Right. It won't be, our first, mid-scale prototype won't be perfect, but we have to do it. Yeah.
In the startup land, we call that an MVP.
Exactly. So that's where I view it. So we want to really build our first mid-scale prototype, continue the research on the fundamental science aspect of decoherence, continue the research at the building block that will, if we, right now we have a double cell, but we will be able perhaps to package even many more modes.
And imagine you're going to need a specialized tool chain for even programming something with 100 qubits, right? I mean, that's not just that's different than just addressing a number of qubits with 2 levels each. That's a totally different type of programming, it sounds like.
Exactly. Yeah. And so we are exploring, I won't say everything, but we're exploring exciting partnerships also with some new industry partners in that space. So I think it's coming together that, we started strong, but we are now really growing and being more and more integrated across the ecosystem. And I'm excited to extend those partnerships with various main industry players. And one of them is IBM.
Yeah.
So with IBM, we are very excited to work together on building larger systems. So that's
and
going to
quantum, and there's you have the benefit of being in the middle of the Illinois sort of quantum explosion that's going on, right?
Yes, Illinois is really
incredible.
It's incredible, and we were so thankful that Governor Pritzker came to the inauguration of our quantum garage. It's nice to know that, even on the political level, you get so much support, and generally quantum gets really strong bipartisan support all around. So this is really great.
Yeah, that's fantastic. Thank you so much, Anna. This has been really great. I very much look forward to the next 5 years of SQMS. So,
well, thank you very much for your kind words, and we are excited to come back here in 5 years and tell you even more exciting stories.
Excellent. Thank you.
Thank you.
That's it for another episode. Thanks for listening. Thank you to Dr. Grassellino for her time. Thanks to APS and Quantum Machines for their support. The podcast is a production of The New Quantum Era, hosted by me, Sebastian Hassinger, with theme music by Omar Costa Hamido. You can find past episodes on www.newquantumera.com or on Blue Sky at newquantumera.com. If you enjoy the podcast, please subscribe and tell your quantum curious friends to give it a listen.